This video covers lenses. So first off, we're going to look at two types of lenses, convex and concave lenses. To remember these, you can think of two spheres interacting with each other to make a convex lens where you have a bulge on both sides, or a concave lens where it looks like it's concaving on both sides. Now let's first look at a convex lens. This is traditionally used in magnifying glasses. The center of curvature equals two focal lengths, so the distance of a focal length is from the lens to half of the center of curvature. So make sure to write this equation down. So a convex lens can be thought of as a triangular prisms at the top and the bottom and a rectangular prism in the middle. So we said, like prisms, less to more, meaning we're going from less dense material to more dense material, we're going to bend towards the normal. And if we move from a more dense material to a less dense material, we're going to bend away from the normal. Again, the normal is a line that's perpendicular to your surface. Now, if we think of the middle portion as a rectangular prism, then light coming along a normal or perpendicular to the surface is not refracted. And any light coming in at an angle does have a small shift in the emerging light, as shown. But this shift is so small, we're going to actually assume that this is not going to be a factor. So again, convex lenses are converging lenses, meaning that the light converges or comes together at the focal point. So just like last year, we're going to do ray tracing, which means that we're going to draw two lines, one that is parallel to the lens and then goes out through the focus. So again, we see the blue line here. And our second one is going to go through the center and then go straight through. So our image will always be drawn from this line in the middle here down to where these lines converge. Now you've seen this equation before. 1 over the focal length is equal to 1 over the distance of the object plus 1 over the distance of the image. Remember, when you are doing this math, you have to get the inverse afterwards. Now we can also look at our magnification, which equals the height of the image, again, I is for image, over the height of the object is equal to the negative of the distance of the image divided by the distance of the object. Now, this right here is referring to the image height. I know it looks like it's part of that 2f, but it's not. Now let's look at what those values mean. If we have a positive focal, then we have a convergent optical instrument, meaning that we're dealing with a convex lens. If we have a negative focal, that means we are dealing with a divergent optical instrument, meaning a concave lens, which we'll see at the end. If we have a positive height of the object, which is normally the case that we're dealing with, that means that our object is pointing up. That's usually on the right-hand side, and it's usually above our middle line down the center. Again, if we have a negative object, that just means that it's pointing downwards or that it's inverted. Again, this is rarely the case. So those mean the same thing in height of the image. If we have a positive height of the image, it is upright. If we have a negative height of the image, it's inverted or pointing down. These are a lot more common. Again, if the height of the object is usually positive, then our magnification is going to be the same sign as our height of the image. What this means is what we're actually looking at is the absolute value of these numbers. If it's greater than 1, the image is larger than the object. If it's equal to 1, then they are the same size. If it is less than 1, then it is smaller than the object. Again, what we're doing is we're comparing the images to the objects. For our situations, the distance of the object will always be positive. What that means is it's always located on the left-hand side of the lens. Now we can actually have two different values for our distance of the image. If it's positive, then this is known as a real image, which can be projected onto a screen. If it's negative, then it's known as a virtual image, which cannot be projected onto a screen. Now, you don't have to be writing all this down because you're going to do it again in class, but it's important that you include this piece. So right now we're looking at a convex lens, and we're looking at an object located beyond 2f. So when the object is outside of 2f, the image is the opposite. The image is inside of 2f, and it is also smaller than our original object. If it's located at 2f, then the image is going to be the same, meaning it's also going to be located at 2f, and it will be the same size. When my object is between f and 2f, then it's actually going to go opposite. What that means, it's going to be beyond 2f, and it's going to be larger than my object. And again, we've seen this situation before. When it's at f, that means my lines are going to be parallel. So you can say that the image is located at infinity, max magnification. But the opposite is also true. If the object is at infinity, then the image is at f. Now we look at the situation where my object is located inside of f. What happens is that the image goes upright. You can see that my lines will not converge on this side, so what you actually have to do is backtrace the rays. So what that means is you've already drawn them, now you're just going to trace them backwards, because they will converge at this point. This image will be very large when the object is close to f. This is also known as a virtual image. It's going to be on the same side as the object. So now we're going to look at concave lenses. Again, these are lenses that are concaved on both sides. The center of curvature still equals 2 times the focal length. And the focal length is the distance from the lens to f. Now, these particular types of lenses are divergent lenses, meaning when the light comes in, it actually diverges, goes away from our lens. Concave lenses all create virtual images, so no matter where the object is, you will always get the same diagram, meaning that the image will always appear on the left-hand side or the same side as my object. Now, for this, it's going to be really important that you backtrace. So again, what that means is you're going to draw your blue line. It goes parallel to your middle line down here. When it hits my lens, it will diverge. But again, you can't see that it's going to converge on the left-hand side. My other ray, the second one, is going to go through the center of this lens. And then you're going to see that if I were to backtrace this blue line, they actually meet at a certain point, and that's where my image will be created. Again, all of these diagrams will create virtual images, meaning they cannot be projected onto a screen.